Welcome to today's session. In today's session, what we do is we just quickly go through the basics of probability what we discussed previously. Then we'll discuss the concept conditional probability and Bayes theorem, and also we'll set the context for one of the very popular classification algorithms in machine learning, that is naive Bayes. Now quickly we revise the basics of probability what we discussed. So first one is the definition of probability, that is P of A equal to M by N. Right? So where N is the total number of cases or entries in the sample space, and M is the number of cases which are in favor of the event A. So this is the basic definition of the probability. Even though we discussed three types of definitions related to probability, this is the one most of the times we are going to use. And the second one is, if A is an event, then A bar is its complement. So where the probability of A complement equal to 1 minus P of A. That means probability of an event plus probability of its complement is always 1. And third point is, probability always lies between 0 and 1, including 0 and including 1. So when, as discussed in the previous sessions, if P of A equal to 0, then it is impossible event. Right? If P of A equal to 1, then it is an event which is going to happen certainly. That's why it is called as a certain event. And other and very important relation which we use in most of the times when we try to solve numericals. So that is P of, if A, B are any events. So here no restriction what we are imposing. Any events, A, B are any events, then P of A union B equal to P of A plus P of B minus P of A intersection B. So A union B is nothing but the probability of happening of at least one of these events. That means A can happen, B can happen, or both can happen. Right? And intersection is nothing but happening of both the events. Right? So it is probability of happening of both. So this is one of the important relation which we use most frequently when we try to solve numericals. Right? Okay. So and other two kinds of events we discussed, that is, one is mutually exclusive and other one is independent events. So what are the conditions related? If A, B are mutually exclusive events, so that means mutually exclusive means there is nothing common between the two events. That means nothing but A intersection B equal to null set. Okay. So then, so same like, so here this becomes 0, right? If A, B are mutually exclusive, then A intersection B equal to 5, then its probability becomes 0, right? So then simply it becomes P of A union B equal to P of A plus P of B. Right? So, and next one is independent events. So what is the condition to say two events are independent? If A, B are independent events, then P of A intersection B equal to P of A into P of. So this is nothing but probability of joint, right? Probability of the joint P A and B is equal to probability of separate events, so the P of A into P of B. Then they are called as independent. So here it is if and only if A, B are independent events, then this condition holds good. For any two events, if the condition holds good, then we call the events as independent events. Right? So these are the few important points we need to remember always when we start moving towards probability and the next. So coming to the next, suppose here if we consider this example, right? Now this is the data what we had, right? Suppose if we consider the present scenario, so based on the data already available, right? So suppose a person, first person whose travel history, that is he is traveled from Spain and no fever, no cough, and the test proves that it is negative. Similarly, Italy, yes, yes, then positive, like this. Right? So now, so we need to know, now this is the data already available with us, right? This is the data already tested and available. Now we need to have one kind of approach or one kind of understanding. If we want, then we want to find if the travel history says pain and fever yes and cough is yes, then what is the expected one? Is it going to be negative or positive, right? So this, I repeat, this actually the information what we had related to six people are already the test done on the in laboratory, right? So based on this history, if any new combination comes, then so what is the expected outcome? Is it going to be a positive or negative test? Right? So what is the advantage with this? What is the advantage of having such kinds of understanding? Now, suppose based on the past history, for this given input, if it says it is positive, then we can ask the person to go and have the test to find out exactly what is the situation. Right? So to understand or to answer such kinds of scenarios, we need some of the concepts, right? So where without doing the test based on the past history available, then we use some probability concepts to understand for a given set of inputs what is the expected output. Is it going to be positive or negative? But here, since this is some kind of estimations or expectations where we come out with a conclusion with a probability. What is the probability that a person whose travel history says pain and fever, yes, cough, yes, then what is the probability that he will test positive or he will test negative? So based on the probabilities, we can come out with a conclusion, right? So this is the scenario, this is the context where we go further and see some of the concepts which helps us to answer or to understand such kinds of scenarios. Okay? And similarly, so this is another kind of scenario. Same kind of. So these one or two examples sets the context for the topics which we are going to discuss. So this is the history. So from the past records, depending on the weather, so whether the play took place or not. So this is the data. And now we want to find, so tomorrow it is expected that the weather is going to be sunny, right? So then whether play happens or not, right? So then if we are able to find a probability that the play happens or play is not going to happen, right? So based on the past history, then it helps us to understand or estimate so whether tomorrow there will be a play or not, right? So accordingly they can plan for it, right? So this, if you see here, so here what we are doing is we had data available from the past, and using that we are trying to find out the probabilities for the future events, right? Okay. And similarly, this is another example. So the data, so some features like so fruits actually long, sweet, yellow. Right? So there some data what out of some fruits that is tested as from the data what we had is, so if it is a long, sweet, yellow, then it is orange, otherwise banana, otherwise like this, right? So this is the data. That's what we call as for these features. Then we are able to say whether it is a orange, banana, or any other kind of fruit. Okay. So based on this data or history given, if suppose any new data comes, that is a new fruit whose features are long, sweet, yellow, so then this is expected to falls under which category or which class? That is it going to be orange or is it going to be banana or others? Right? So these are some of the uh, instances or examples where so we can answer this with the help of some probability concepts. Okay. Right. So what we do is we'll go for one concept called as conditional probability. Right? So we know already we discussed probability. So now what is this conditional probability? Right? Now for instance, now consider an example. Now 1,000 persons are there, right? So what two ways we are doing. One is we are asking these 1,000 persons go for diabetic test. Right? So the thousand so diabetic test is performed on 1,000 patients, and the output is out of these 1,200 are diabetic. Right? Now, based on the previous discussions, now we can find what is the probability that a person is diabetic. Right? I repeat. So, what is the probability the person is diabetic? So, sample space contains 100, out of which 200 in favor of diabetes. So, therefore, the probability is 200 by 1,000. Right? It is a simple thing which already what we are familiar with. But here the thing is, next after this diabetic test, what we are doing is we are asking these 200 people to go further and have BP test. Right? Okay. So out of these 200, it is identified 100 people are having BP also. Right? That means if you see out of 1,000, so 200 are having diabetic. So next, that means these diabetic patients are going further for BP test. Right? So finally, you will have 100 people. Right? So this 100 is what? The 100 people or 100 persons who are having BP and also diabetes. Right? Clear? So now we'll take in this same in another way. So take the same 1,000 persons and we'll ask them to go for BP test first. Right? So out of 1,000 persons, 300 people are identified with BP. Right? Now after BP, we ask them to go for diabetes test. Right? Out of 300, it is identified that 100 are having diabetes. Right? So finally, if you see here are either the first case, what we are having the conclusion. So we identified 100 people who are having BP as well as diabetes. Right? Now similarly here we tried what is the probability that a person is diabetic. Similarly, we can find what is the probability that a person is having BP. So very simple, right? Out of 1,000, 300 are having BP. Therefore, the probability is 300 by 1,000, right? So nothing new here, right? Okay. So, but here if you see the process, here the first thing happened is diabetes. Next thing happens is BP, right? That means before going for this BP, there is already an information that they are all diabetic. So next, in the second example, so we already information is available that they are having BP and they are going for diabetic test, right? So now such kinds of scenarios, if we consider, then conditional events comes into picture, right? So conditional events means here, in this case, so first they are diabetic, right? Next they are having BP. So before going for BP, already this is happened or this is already tested that they are diabetic. Right? So this is what we call as a conditional event, B given D. That means D happened first follows B. Or B happens with a condition that D is already happened. That is they are already diabetic. Now take the second case, right? So already these are BP patients from which we are trying for diabetes, right? Right. So these, now if you see here, this is what we call as B given D, and this is what we call as D given B. So here, what is the difference between these two? Both are conditional events. Difference is here D have diabetes first follows BP. BP first follows diabetes. So these are all called as conditional events. But if you see, when we consider conditional events, the final output is nothing but intersection, right? So final end outcome is the people who are diabetic as well as having BP. Right? So that means if we consider events, both are the same events. Right? But now we want to find probabilities of these conditional events. Then what happens? Right? So we'll see it. Now same example we can take smokers, then identified whether they are having cancer or not. Next, already cancer patients and we tested whether they are smokers or not. So here smokers is the first thing happens followed by cancer. Right? So in this case, cancer first followed by smokers, right? Or smoking habit, whatever. Right? Now, so this is what we call as, right? So these are all called as conditional events. So B, it is generally we read it as BP given that diabetic. Here diabetic given that BP. That means this is the first event happens follows by this event. Right? So, otherwise we can I'll write like this. Suppose if we write A given B, right? This week we call this as A given B, where B happens first followed by A. Other one is B given A. So these are all called as conditional events. Now we'll take how to find probabilities. Right? Now take the same example. Now we want to find out what is the probability that a person is having BP given that he is already diabetic. Right? So in this case, how to do now? So this is the the latest event happened, right? So BP. So already this is happened, right? That means now here we are doing this, we are going for this event where the sample space reduces to this. Right? That means we are selecting BP patients from these diabetic patients, right? So therefore, probability of BP given that diabetic is, so sample space is 200, out of which 100 are in favor of having both, right? So 100 by 200. Now if we take the second way of doing, so first BP follows diabetes, right? So so the sample space is this, that is people with BP from which we are going for diabetic, right? So therefore the sample space now reduces to 300, and where the numerator is nothing but 100. Now I think we can see it clearly. So what is the reason for us to say that these two probabilities are not same? In case of events, both are the same. In case of probability, they are not the same because the sample space differs here, right? So this is the sample space here, this is the sample space here. Right? So this is how the conditional probability can be understood. Now, is there any way that we can draw some expressions for this? If you see here what we have done, we can write like this. Probability that BP given that diabetic. So then probability of BP and diabetic by, because this is the sample space, right? So that comes first, right? So probability of BP given diabetic is probability of BP, and that means intersection here by P of diabetic. P of diabetic given that BP, then it is sample space is nothing but BP, right? Then numerator is nothing but the intersection of diabetes as well as BP. So like this we can have the representations for conditional probabilities, or more clearly the way that we are going to use when we deal with numericals. So P of A given B equal to P of A intersection B by P of B. So very simple here, right? So B is the sample, first event happens, right? So that is the sample space, so where its probability comes P of B, right? So from B we are selecting A, right? That means numerator results in intersection. So similarly B given A, so where A is the sample space, right? So therefore P of A comes here. So numerator is the same, right? So from A we are selecting B, that means nothing but A intersection B. Right? So this is how we can understand conditional probabilities as well as probabilities of the conditional events. Sorry. Okay. So now another term that we define is multiplication rule of probability. So this is nothing new here. So this is already what we discussed. P of A given B equal to P of A intersection B by P of B. So no need to remember this formula, very simple. So this is the first event happens, therefore this comes in the denominator. Then numerator comes combination of both. Similarly here. Right? Now from these two we can take P of A intersection B, right? So if we go for cross multiplication, right? So from the first one what we get is P of A intersection B equal to P of B into P of A given B, or the second one is P of A into P of B given A. Right? So now, so just we need to observe this closely. So P of A comma B or A intersection B equal to the first event happens what? A, right? First event, right? First event happens this way, followed by second event, right? So similarly here, first event happens is B, so next event follows A, right? So this is what we call as multiplication rule of probability. So now next question comes, next doubt or question comes is there any way that we can extend it further? If you see the discussion till now, whatever we had is we confined our discussion only to two events, but in most of the applications we can see is a flow of events, right? First one event happens, next from that sample space another event happens, from that another event happens, like this, right? So the question here is whether this multiplication rule of probability is scalable or not. That is, whether this can be applied to many events, right? So that is the question. Okay. Now, very simple. If we understand this clearly, now this is what we discussed, right? P of A1 intersection A2, right? Suppose A1 is the first event happens, so P of A1, right? So A1 happens first, right? So here conditional probability comes A2 next. So A1, A2 happened. Now next third event is joined, right? Then if you see here P of A1, P of A2, A1 already over. So A1, A2 already happened, right? So that's why A1 intersection A2. Next new event joins is A3. Now we can guess. Suppose one more event A4 joined, right? Then what happens? So this will be there first event. So A1, A2, this combination will be there. So A1, A2, A3 combination will be there. So next what happens is new event that joins is A4, right? So where already the three events are already over, right? Already happened. A1 intersection A2 intersection A3, right? So that means what we can say is this multiplication rule of probability is a scalable one. So this way of doing is a very important when we go through some of the concepts in machine learning or AI kind of stuff. Right? So now if we generalize it, A1 intersection A2 and so on up to intersection AN. Right? The same generalization. A1 first, so next A2, A1, A2 over, next A3. Like this continues A1, A2, so on, AN minus 1, next last event is AN. Right? That means, so, so this is multiplication rule and it can be scalable, which can accommodate as many events as possible. Okay, just 1 minute. Right. Now, so one more conclusion we can draw based on the basic definition and the knowledge what we had is, so this already what we have been discussing, right? P of A given B equal to P of A intersection B by P of B. Here suppose A, B are independent events, right? If A, B are independent events, we know, right? Then this P of A intersection B can be written as P of A into P of B. Then by P of B gets cancelled, therefore P of B. That means P of A given B equal to P of A, right? So P of, that means probability of the conditional event is nothing but probability of the latest event happens. Right? That means it is not going to depend on this, right? Right? Similarly, if we take the other way, so P of B given A equal to same way P of A intersection B by P of A. If A, B are independent events, then we write this as P of A into P of B. So it gets cancelled, then we'll get this, right? So from this, what is understood in a conditional event, if the latest event is not depending on the event which is already happened, right? That is what actual, right? So probability of this conditional event is equal to probability of latest event. In this case also, right, probability of this conditional event is nothing but probability of latest event. Then they are called as independent events. Other way around, right? If A, B are independent events, these holds good, or these holds good, then also we call them as independent events. Okay. Now, I think so we clearly understood. So, what is a conditional event and how to find conditional event and generalization of multiplication rule. So, with this understanding, we'll try to solve one or two problems to check our understanding. Right? So, one is from a hospital data, it is observed that 55 patients are diabetic, right? And 75 patients are with high BP and 35 are with both. So that is they are having high BP as well as diabetic. So two events here, right? So one is patients with diabetes, patients with BP, right? So then they are asking us to find the following things. One is what is the probability that the patients are diabetic as well as high BP? Right? And second one is, if you see here, so what is that we have to find here? What is patients who are diabetes, who are having diabetes as well as high BP. That means it is nothing but simple intersection, right? Diabetes intersection high BP. Second one, the patients with high BP, right? The probability that the patients with high BP, knowing that they are diabetic. That means here, so this is a conditional limit. Already they are diabetic. So what is the probability that they are having BP? Right? So of the people who are known to have high BP, right, find the probability that they are not diabetic. That means the first information or event happened is BP, right? Then what is the probability that they are not diabetic? That means diabetic is D, then D complement. Okay. So now we'll see how to solve this problem with the understanding whatever we had till now. Okay. Right. So as discussed earlier also, instead of depending on the formulas, whenever it is possible, better go with the Venn diagram approach. So here, so this is diabetic, this is BP, and 35 are having both, so 35, right? So this 35 is intersection, that is diabetes as well as BP. 55 are diabetic, so already 35 are into intersection, therefore left over is 20. So 75 patients are with high BP, out of 75, 35 are in the intersection, therefore 40. Now we can validate here. 35 plus 20, this is number of patients who are diabetes, that is 55. And 40 plus 35, 75 is nothing but the number of patients who are diabetic. Right? So now, so first thing if we take the patient, what is the probability that the patients are both diabetic and high BP? So it is a very simple thing, that is P of D intersection P, right? So the total sample space, if you take 45, 35, 20, therefore 95, out of 95 patients, 35 are having both, right? So there it gives 0.36, whatever it is. So it is no conditional probability here, it is simple probability definition we used, right? Yeah. Next, second example, second thing we should take, right? So I think now it is very clear. So what is the first event happen? What is the first hand information, right? So first hand information is already they are diabetic, right? So what we have to find, what is the probability that these diabetic patients are having BP, right? So that means it is something related to conditional probability, conditional events, etc. Right? So then immediately we write, so probability of first event happens is D, next event happens is B. And we know the formula, right? Just now what we discussed. So numerator is the joint and denominator is the first event happens, right? Once this is there, now B intersection D, what is its probability? So 35 out of 95, so 35 by 95. So only diabetic. So how many are there? Not only, how many patients are there? They are diabetic, right? 35 plus 20, therefore 55, 55 by 95. So this is the conditional probability. Right? So what is the probability that a person who is diabetic will also have, is also having BP? So it's 0.6363. Okay. Next, third one. So here first information is the patients are already having, they are with BP, right? So they are with BP, then what is the probability that they are not diabetic, right? So that means, so first event is B, second event is complement, that is D bar. So then P of D bar intersection B by P of B, right? So D bar intersection B means what? So BP but not diabetic. So they are having BP but not diabetic. So that is what we have been discussing. Instead of depending on formulas, if you see the table Venn diagram here, right? From the Venn diagram, so how many people are there who are having BP but not diabetic? So now this total is BP, right? This total is BP patients, out of which 35 are diabetic also, right? So but here what we want is exclusive BP, right? Exclusive BP is 40, right? So therefore 40 by 95, and BP, total number of people who are having BP is 75, therefore. So like this we can solve problems, right? Okay. But another way of doing is, if any confusion with respect to complement events, actually P of this is also complementary event, right? P of D bar given B is nothing but 1 minus P of D given B. Right? So we know how to calculate this by using our straight formulas, right? So P of D given B is D intersection B by P of B, right? And substituting all these things. So this is other way that we can try to solve the same problem. So depending on our understanding, we can try to use any one of these approaches. Okay. Next one, another example we'll try so that it becomes very clear with respect to the concept. Consider the families with 3 children. And here, if the first 2 children are girls, right? So family with 3 children, and first 2 are already girls, then find the probability that third is a girl, the third is a boy, and the family has at least one boy or at least one girl. Right? So here if you see, what is there any conditional probability involved here? Yes, here already information we had is first two children are already girls, right? This is already happened event. We need to find what is the probability that third is a girl, what is the probability third is a boy, like this. Therefore, so this can be solved with the help of the concept conditional probability, right? Okay. So how to solve? We'll see it. Okay. Now, so family with 3 children, right? So to find probabilities, we can see what is the sample space corresponding. Right? So we'll have various combinations, right? So all boys, first 2 boys and girl, like so various combinations. That is so. Right? So these are all common, all boys, all girls, first 2 boys followed by girl. So total we have, right, 2 cube, that is 8 in the sample space. Right. So now we'll consider the event. So this is the first event happens here, right? Having first two children are girls. Right? So let us consider this as an event A. A is an event where the first 2 children are girls. Then it's very easy, we can find its probability, right? P of A equal to, so total is 8. And what are favorable cases? First 2 children are girls. So this is one favorable case and this is another favorable case, right? So therefore 2 by 8. Right? Next, another event, right? Right. So another event what we is that B be the event where third is a girl, right? Then what is the probability? Third is a girl out of 8. So what are we need to see? What are the favorable cases where third is a girl? 1, 2, 3, 4. Right? Sorry. So therefore it is 4 by 8. So similarly, C is the event where third is a boy. In the same way, so 4 combinations which are in favor of it. Therefore 4 by 8. So with this data available, then we'll see what is that we have to find. Right? So first one is already 2 girls. So what is the probability that third is also a girl? That is probability of B given A, where B is having third is also a girl. Right? So this is a conditional event. Right? And immediately we recall, so the corresponding formula, right? P of B intersection A by P of A. So P of A already we calculated, so 2 by 8. So B intersection A means what? A is 2 girls, B is third is a girl. That means all 3 are girls. So out of the sample space, only one possibility which is in favor of that intersection, that is 1. Therefore it is 1 by 8. So 1 by 8 is the probability corresponding to this, 2 by 8 is probability corresponding to this, therefore it is 1 by 2. So second one, same. So first 2 are girls. What is the probability that the third is a boy? Right? So now same formula. So C given A is C intersection A by P of A. So P of A already what we calculated. Right? So C intersection A means what? So A is girls, that is already two girls, and third one is a boy. Right? So only one combination like this, therefore this is 1 by 8. So therefore the probability is 1 by 2. So like this we can use the probability concepts. Right? So other one is, so probability that the families has at least one boy, and actually it is end. The families has at least one girl. Right? Suppose if we take E1 as the event related to one boy, E2 as the event related to one girl. So now we have to find P of E1 intersection E2. So how to find this? Now we know probabilities. P of E1 we know. Right? P of E2 we know. So out of 8, so we can find out the cases where at least one by except all girls, all are in favor of this event. Therefore 7 by 8. Similarly, here also except all boys, so all are in favor of getting at least one girl. Therefore 7 by 8. And it is understood that P of E1 union U2 equal to 1. And we know the formula, right? This the what we have been discussing. P of A union B equal to P of A plus P of P minus P of A intersection P. Now we plug in the values. So 7 by 8, 7 by 8, and this we have to find. So simple simple algebraic way of doing the things gives the probability as 3 by 4. Okay. So like this we can try to solve the problems where we use the concept conditional probability and its corresponding expressions, formulas, etc. Right. Okay. So next we go for one concept called as total probability. So this is something where we'll take the conditional basic discussion related to conditional probability to the next level where we go for total probability. So what is this total probability? Right? Suppose consider to understand this concept first we'll go through one example. Right? Suppose an individual has three different email accounts. Right? So account 1, account 2, account 3. So out of which, so this first one is the primary account where maybe office account kind of thing where most of the communication comes to this mail account. And second one is another account where 20% of the mails, total mail out of total mails, 20% communication comes to this mail. Third account where 10% of the mails comes to this. Right? Right? So three mails. So if you see here, A1, right, 70%, A2, 20%, A3, 10%. Right? So next, so based on the past information, based on the information available, so out of the mails that are coming into the first account, 1% of this 1% are spam mails. So this is based on the observation, based on the experience. It is observed that 1% of the mails that are coming into the first account are spam. Similarly, 22% of the mails are spam related to second account and 5% are related to third account. Right? Right. Now you see here. So A1, A2, A3 are mail accounts, out of which, so out of all the mails that are coming, these are the spam mails, right? Spam related to first one. This is spam related to second one. So this is related to third one, right? Now we want to find out what is the probability that a randomly selected message is a spam. Right? So that means, so out of all, we had the information that is what are the percentage of the mails that are coming to first account, second account, third account, and we know what is the percentage of mails or spam related to each and every account. Right? Okay. So generally we will see when we sync various email accounts in our mobile, when we open the mobile, we'll see spam 40, right? The spam 40, right? So that means this 40 is that is showing in the spam is a combination of the spam that is received to the first account, second account, third account, right? So now we want to find out what is the probability that a message received is a spam, right? So how to find? So from this diagram, very simple, right? So this plus this, right? So this plus this gives probability of E. Suppose E is some event related to mail which is spam, then we have to find probability of E, right? So this is right total probability. This is what how to find this actually how to find this total probability, right? Now if you see here this from this diagram we understand this plus this, right? So this means what? This is A1 intersection E, right? This is A2 intersection E. This is A3 intersection E, right? So if we add these three, you will get P of E, right? Let's see here. Next slide, right? So now I think it becomes very clear. So P of E equal to P of A1 intersection E, right? P of A2 intersection E, P of A3 intersection E. And actually if you see why we use it plus here, because they are mutually exclusive, nothing common here. This is one event, this is another event, this is another event, and all these three are mutually exclusive. So because of that we use the plus between the probabilities, right? Okay. So next, how to find this? So we know from the multiplication rule of probability, P of A1 intersection E can be written as, here if you see, if you remember the multiplication rule of probability, we had two ways of writing it, A given B into P of B or B given A into P of A. Right? Which one we have to use here? So it depends on here A1 happened first, right? Followed by E. So that's why here P of A1 into P of E given A1. Right? Similarly here P of A2 into P of E given A2. So P of A3 and E given A3. So very simple, 70% into 1%, 20% into 2%, 10% into 5%. This gives 0.016. So what is this 0.016? So out of all these mails, spam information, whatever we had, if we randomly selects a message, or the mail, what is the probability that is going to be the spam? Right? So this is what we call as the total probability. Okay. And so one way is we can write like this where we can understand, or other way is we can write like this. So A1 is the first mail account, follows spam, that is 70%, right? And 1%. So second mail, that is 20%, next follows spam, 2%. So third one, 10%, follows 3%. So now very simple. So the product of these branches, 70% into 1% and 20 into 2 and 10% into 3%. So that gives the sum of these products gives the total probability. So depending on our understanding whether we can use this approach or we can use this approach when we try to find the total probabilities. Okay. Okay, next comes, so not this is not the end of the discussion related to this. Now next comes is, so we had, right, what is the probability that a mail selected is a spam, right? That is fine. But next thing is this spam, whatever we are getting is because of which account, right? Whether this randomly selected spam is, what is the probability that this spam mail is related to first account, related to second account, related to third account, right? Okay, so that information is very very important, very useful, because if we know that probability, wherever that probability is high, then you can think that, so this the second, suppose second account probability is more, then you can understand that, so this second account is more prone for spam, therefore you can delete it, right? So like this, these probabilities helps us to understand and to take a decision. So how to do it, right? We'll see it like. So this is now, for example, what is the probability that a randomly selected message is a spam and it is from account 2, or it may be account 1 or account 3. So how to find it, right? So now from earlier discussion, we know what is the probability that the mail selected is a spam, right? This is, right? P of E we know, right? Now what we want to find, the spam mail is selected, then what is the probability that it is from second account, right? So from, if you recall the basic definition of conditional probability, this can be written as P of A to intersection E by P of E, right? P of E means this complete, right? Complete, right? Out of which, so which is in favor of this A to intersection E, right? So this comes in the numerator, right? This is, so P of A2 into P of E given A2. Suppose if we want to find A1, then this comes in the numerator. If we want to find this, then this comes in the numerator. So like this, we can use this concept to find the probabilities of having a spam mail because of first account, because of second account, because of third account. So this understanding is nothing but one of the very popular, very popular concept, that is Bayes theorems. So very important, very popular nowadays. So this is one of the beautiful algorithms people are using in machine learning based on classifiers, naive Bayes classifiers, etc. Okay. Okay. Now the same understanding, whatever we had, can be put in the term in the in statement. Right? So let A1, A2, AK are mutually exclusive and exhaustive events. Right? So what is meant by mutually exclusive exhaustive events? Right? So we know mutually exclusive events means intersection of any of these combinations equal to 5. That is what we have seen, right, in the previous example what we have taken, right. So here A1, A2, A3 are mutually exclusive and exhaustive. There is no other possibility of having A4. Right? That means this A1 union A2 union A3 and so on is equal to the sample spaces. Right? I think these are two very important conditions where we can apply Bayes theorem. That is, the events A1, A2, A3 are mutually exclusive. There is no common. And these are the exhaustive events. Exhaustive in the sense here, thus union of this A1 union A2 union A3 is equal to S. So A1, A2, AK are mutually exclusive and exhaustive events. So then E be any other event, right? So like what we have been discussing, right, the previous one. So A1, A2, A3 are mutually exclusive exhaustive, and E is any event, other event, right? This is E. That is what is meant here. So then, what is the probability that P of AI given E equal to P of AI into P of E given AI? Right. So the same. This is nothing but the total probability. Total probability, and this is the probability which is in favor of this event. suppose I equal to 1, A1 given E equal to P of A1 into P of E given A1. Right? So how to prove it? So in most of the exams, they may ask us to prove state and prove Bayes theorem. So once we had this understanding like this, if this is very clear, then it is very easy to prove this Bayes theorem. Same like what we did it in, we applied the logic in problem. Now we are using it to prove, right? So A1, A2, A3, and so on are mutually exclusive and exhaustive events, and E is an event out of it, where we'll find A1 intersection E, A2 intersection E, A3 intersection E. Now E is nothing but sum of, right, A1 intersection E, union of A2 intersection E, A3 intersection E, and so on, AK intersection E. Right? So as discussed, this event, and this event are mutually exclusive. There is no common here. This is separate event, this is separate event, this is separate event. If separate, then union is nothing but addition, right? So then P of E is P of this event plus P of second one, P of, and so on. Now by using the basic multiplication theorem of probability, P of A1 intersection E can be written as, generally when we try to write this, they will get a confusion whether it is A1 first or even, but here it becomes very clear. A1 is the first event, follows E, right? So P of A1, A1 follows E. Similarly second, similarly third, and so on. Now we can write this with summation I equal to 1 to k P of AI, P of E given AI. Right? So this is nothing but what we discussed with an example also. This is nothing but the total probability. Now we want to find this, right? P of AI given E. Right? So P of AI given E is nothing but our basic definition. P of the intersection of both the events by the denominator. Now P of AI intersection E is nothing but, we can write like this, right? So, and P of E is nothing but total probability. Right? So this is how the Bayes theorem can be proved. So once we are very clear with respect to concept, it is very easy to prove, or it is very easy to write. Now, it's actually, what is the use of this? Is there just to have some interest in this concept? So, what is the use of this understanding? Right? Suppose, now if you take this, assume that 3 reasons are there which may cause cancer. So, maybe smoking may cause cancer, or pollution may cause cancer, or because of genetical disorders. Right? If you go to any cancer hospital, it is possible for us to have this data, right? So how many smokers are admitted, out of which how many are have cancer? That is, out of the patients admitted, the percentage of the people who are smokers, right? Percentage of the people who lives in polluted areas, who are having some genetical disorder from the family history. So now out of this, how many are having cancer? Out of these smokers, how many are having cancer? How many are having cancer here? How many are having cancer? Now, suppose if we are able to find, that is, if randomly if we select a cancer patient, what is the probability that he is a smoker? So what is the probability that he is from a polluted area? What is the probability that he is having some genetical disorders from the family history? I think now these probabilities we can find with the help of Bayes theorem as discussed, right? Right? Suppose the Bayes theorem is giving the 0.2, 0.6, 0.2. So I think how to find is very simple. So first we need to find total probabilities. Total probabilities comes in the denominator, right? In case of this, the product of the first branch comes here, that gives the first one. Now similarly here the total probability comes in the denominator and this product comes in the numerator, that gives this probability like this, like what we discussed in the previous problem. So now suppose if we are able to have these probabilities 0.2, 0.6 and 0.2, right? Then it is understood. So what is the main reason for cancer from the data available is it is not the smoking as we assumed, right? It is not the smoking, it is pollution. Right? So now this helps us to understand, to take the decisions, right? Government can look into it. So how to take care of this? Right? Similarly, we can take, suppose it is something like, one more example to have interest, like related to applications of this Bayes theorem. Suppose from the past data, now we had video surveillance, right? So we can capture on a given junction or a given hotspot kind of thing. We can have the data collector, right? Suppose now it is assumed that so accidents happens because of various reasons. One is a drunken drive, so bad roads, right? Or reckless driving, senseless driving, right? So because of which accidents are happening, right? Accidents as well as death, right? So now past data gives, so what is the percentage of accident happens because of drunken drive, bad roads or reckless driving, right? And what are the percentage of deaths, right? Now it is if it is possible for us to find, take an accident, taken a death, what is the probability this is because of drunken drive, or this death because of this BD, bad roads, right? Or because of reckless driving, right? Suppose this probability is 0.6. So by using Bayes theorem, suppose we are calculating this is 0.2 and this is 0.2. Right? So now this data gives a clarity that so on a given place, so most of the probability that accidents are taking place because of drunken drive, right? So now the government can take some measures to take care of this, right? So that's why, so here if you see the entire the understanding related to Bayes theorem is some inferences drawing out of the information that are already available, right? Okay. Now one more example to understand the Bayes theorem very clearly. Now once we are able to understand the application of Bayes theorem, very simple here. Now in a certain town, patients visit doctors in a ratio 6:5:7. So 6 by 6 plus 5 plus 7. Probabilities we want to find. P of A is 6 by 6 plus 5 plus 7. B 6 by 6 plus 5 plus 7. C 6 by 6 plus 5 plus 7. So the probabilities or chances that these doctors will refer the cases to a specialist with a percentage, 45% of the cases, 60% of the cases, 55% of the cases. Now what is the probability that a patient selected at a random visits a specialist? So here visiting a specialist is the second event the happens. So here we need to find P of E. Right? So total probability. In the second one, what we have to find is all combinations. So what is the probability that a person visit a specialist? What is the probability that he is referred by patient A? Dr. A. Similarly, he is referred by Dr. B. Similarly, he is referred by Dr. C. Right? So this is nothing but an application, or this problem can be solved with the help of Bayes theorem, right? So once it is very clear, then very simple, right? Just we can draw the diagram, right? So 6 by 5 plus 6 plus 5 plus 6 by 18, right? 6 by 18, so 5 by 18, 7 by 18, right? So next follows is, what is the probability that A refers? That means it is next conditional event, that is 45%. So B refers, C refers. So now the product, right? This and the product of this and the product of this, adding this gives a total probability, that is denominator, right? So if you next, if you want to find the probability that this is referred by A, this is referred by B, referred by C, so very simple, right? So in Bayes theorem, this comes in the denominator, right? Total probability. If you want to find the probability related to A, this comes in the numerator. If with respect to B, this comes in the numerator. With respect to C, this comes in the numerator. Like this. Very simple. This is the total probability in case of A. So product of these two, product of these two, product of these two. So that means here we can understand what is our understanding. So the C doctor, most of the times he, whatever the case comes here, most of the time he refers to a specialist. Next, B is, so A is the one where the probability is less. He is the one who prefers, whose preference is very less when he wants to refer this to a specialist. So from this we can understand, so better we can go with A instead of going for B or C, because always they will forward this case to a specialist, right? So one more example. So I think once we are very clear with respect to this approach, very simple. 3 machines A, B, C manufacturers this percentage of items, 25%, 30%, 40%. And out of these, so based on previous data, so 5%, 4%, 3% are defective items. So from A 5%, from B 4%, from C 3%. Then if an item is drawn at random and found that it is defective, right? So what is the E here? Getting a defective item, right? So an item is drawn and found that it is defective, that is E. Now what is the probability that it was manufactured by A? That means E is the event happened first, followed by A. So here, so again we have to go for Bayes theorem. Why we have to go for Bayes theorem? Because many events happens, right? A, B, C. If it is only A follows C, then we have to go for the simple and basic definition of conditional probability, right? So once this is very clear, very simple, right? Just drawing the tree diagram approach, right? So A, right? So the first machine 25%, then defective follows is 5%. Second machine 30%, defective corresponding to it is 0.04. Third one is 0.45, 45%, then its defective is 0.03. So multiplying these two plus these two plus these two gives the total probability as we have been discussing, right? Then here what we want to find is a defective item is, what is the probability that is from first one. Then if it is first one, this comes into numerator. Okay. So therefore this is the probability. Okay. So like this, now very easy to, once we understand the problem clearly, if we are able to draw this tree diagram kind of approach, very easy to do it. No need to remember the formula. In general, if we try to remember the formula, there will be a little bit of confusion actually. So here, so like what we started the session. So from a given data, so we want to find, that is, we know that sunny, then what is the probability that play happens, right? So if it is sunny, what is the probability that there is no play, right? Now, so suppose it is a 0.2 and this is 0.8. So how to calculate this? By using Bayes theorem approach. Then we understand, so probability is high here, therefore there is no play based on the past data or past record. Okay. Similarly, this fruit problem, right? So based on the past record, so now the new one is this, right? Long, sweet yellow. What is the probability that it falls under orange? Similarly, what is the probability that it falls under banana? Based on probabilities, wherever it is high, then we say that this new one which is coming into, new data which is coming into, falls under either orange category or banana category or some other fruit category. Okay. Similarly, actually, this is something called a text analytics, what we call as. Suppose we had a one document. This is a movie reviews. I hated the movie. I loved the movie. It's a great and good movie. It's a poor acting, great acting, good movie. Right? So this is already data available. From this, we understand this is a negative review. This is a positive review. This is a positive review. Right? This is a negative review. This is a positive review. Right? Right? So because why you say this hated is something which is a negative sense. Loved is a positive sense. Right? Like right? This is the data already available and we know the classification whether it is a positive review or negative review. Now we want to find out a new document, new one is coming and I hated the poor acting. Right? Whether this falls under positive review or negative review. Right? So this is how the social media platforms works. Whenever the new post comes, it can detect, it identifies whether this is some abusing content, abusing statement, right? So based on the past history, they had it, whether it's a positive comment or negative comment. Whenever a new thing comes, based on the data, based on the training that is happened based on the past data, it categorizes whether the new one is a positive review or negative review, right? And these are some applications. So for all these applications, what we require is a Bayes theorem, what we discuss, with a little bit of modification. That is what we call as Naive-Bayes classifier or Naive-Bayes theorem. So what is that is? For example, here P of C given X. X means here if you take this a fruit example, right? The new one, right? Fruit example is yellow, sweet, long, right? Then we want to find what is the probability that it falls under orange. Right? P of C given X. And we know it is nothing but P of C intersection X and P of X. Right? And we know this is nothing but from Bayes theorem we can write this as P of X given C into P of C. But only problem here is P of X means it is not only X consisting of X1 as well as X2, X3. That means here X is nothing but X1 intersection X2 intersection X3. Right? And these probabilities are not available. What we had is P of X1, P of X2, P of X3. So we know when two events are independent, then we can write P of A intersection B equal to P of A into P of B, right? So here also this is intersection actually. P of X1 intersection X2 intersection X3. Right? So now instead of this, what we want is P of X1 into P of X2 into P of X3. So when we can have this? So when they are independent events, right? If X1, X2, X3, there is actually in the machine learning terminology, they are called as features. And C is called as a class. Right? So this can be used only when X1, X2, X3 are independent events. Right? So Bayes theorem with independent events. So which is nothing but Naive-Bayes theorem. So Bayes theorem, if you take Bayes theorem, put a restriction that X1 in the class features are independent, then it goes towards Naive-Bayes theorem, which is one of the popular machine learning classification algorithms. So this actually to create interest, like why we need to go through the Bayes theorem, right? So Bayes theorem is the base based on which we had Naive-Bayes theorem, which is one of the popular machine learning classifiers. Okay. I think with this we summarize and we close. That is So today, what in this session, what we discussed is the conditional probabilities and how to identify the conditional probabilities. So when more number of events involves, then the conditional probability goes to the next level where it goes for Bayes theorem. Right? So when in Bayes theorem, when we put the condition that the x1, x2, that features are independent, then it goes for naive Bayes classifiers. Right? This is the what we want to discuss in today's class. So thank you. Thank you very much. So we'll end this session.